Welcome back. Thank you, Thomas, for 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 Thank you, Thomas, for welcome back. Thank you, Thomas, for welcome back. Thank you, Thomas, for electrons have just to cross a barrier. And that's what we observe, a change in potential due to these crossing the barrier of this electron here. So we have, of course, this is a superconductor. It's a phenomenon of superconductivity, so we have to keep this on the very, very low temperature. And we have now a system that can record many of these, have many of these sensors that we call a SQUID. Superconductive quantum interference device, something like that. I don't remember perfectly. So in the sense of the physics behind the EEG and MEG inverse problem, what you have is normally this neuron produces this current source, point current source, and this source will propagate through the conductor and create these different potential here, and because there is a current, this will create a magnetic flux around this, so a magnetic field around this current, and then you can record variation in flux across the coil, right? So what is the physics of this? The first thing is that you have to define what is this current source. So you have to treat this, and you have to go to the theory of Maxwell equation, and then start to use it and make assumptions about the Maxwell equation. That's what we are going to do here very quickly. So for those that are really didn't take the physics, probably physics 2, probably you just close your eye for a minute. I will not use much of this time here. But you have here, this is the electric field. We call this microscopic electric field, and this is the magnetic field. They are just vectors, but vectors that change when you change the position. So in this position here, this vector is in this direction, but a little bit far away from here, or just close to this, the vector change. So the direction of the vector change when position. We call this a vector field. The field is because of this variation. So what you have here is that anything, whenever you have a vector field, you can characterize the vector field by two things. One is where the line of the vector field are originated. And this is what we call the sources or the sink. So if you have line that cross, that means there have to be there a source or a sink. And the other thing that you need to have very well described, where the vector field curve. So these two concepts are described by this thing that we call here the divergency, and this operator here that we call the rotational or curve. So what I'm saying here is that wherever you have a charge, you have a source for electric field, and what I say here is that whatever the magnetic field change, that will curve the electric field around. And of course, we know that there is no source for magnetic field, there is no monopolar source for magnetic field, and we know that wherever you have a current of any type, this is ohmic current, this is the neuronal current, and this is the displacement current. Whenever you have a current, then it will curve the magnetic field. And that's all about this Maxwell equation. So what you can do is, first, this is microscopic. You have to take them to a next step, which is the macroscopic Maxwell equation. And then we have here that this equation transformed in a way that what was before an electric field now is a displacement field, or electric displacement field, that include the capability that have tissue to accumulate charge in the form of capacitor, which we call this electric permittivity. And now what we're saying is that this is the free charge what changed this magnitude, and then you have a couple of other things that remain almost the same. The only thing is that this B, capital B, means the average of the small b, kind of statistical average. And then you have here that this JP in capital letters means a kind of macroscopic sources that we are going to talk a little bit later. The next approach we're going to make is that we know that that the electric field that we are dealing with, the phenomena that we are dealing with, is in between 0 to 1 to 10 kilohertz. So it's not fast as we know, for example, how radio frequency, which is the range of frequency for radio frequency activity, for microwaves that is in very, very high or very low frequency range. We have a very specific frequency range for the activity that happens inside our brain. And in this case, you can assume, or have been demonstrated, that the variation of a magnetic field, the curve that the variation of magnetic field made on the electric field are very, very small. Actually, it will practically, you will be able to notice this curve if you have an area of more than 65 meters. That place you can then realize that there is a curve. But if you are in the space confined by our brain, our head, you will not be able to notice this curve. And the second thing that the second assumption you're going to make is that this term here is very small with respect to these two. Taking into account characteristic of our brain biological tissue in general, we know that this always is these two are always larger than this one. So when you get these two assumptions, you come to the quasi-static approach, and this with a little bit of knowledge of mathematics, you know that then the electric field have to be defined as a gradient of a potential, and using these two, you come to with the first equation that we use in EEG and MEG, which is the Poisson equation. Now you have to introduce a gauge, because you know that there's always an uncertainty in defining these two potentials, and we use this particular gauge here, and then you get the final equation for the magnetic field. So forget about all this math. Whatever, if you are going to use, and you're going to work in an EEG, MEG inverse problem, and you're even a theoretician, probably you can start from here. Just throw the other thing away. And I think some people already take it literally to close their eyes. So the solution of this equation here is given by this integral, where this is the current generated by neuron, and this is the potential that you observe at some point on the scalp, and this is the magnetic field. So the common factor here is this little term here that we call this the green function. So we're going to use a little bit some property of this green function, especially because how big is a mini column or a micro column in your cortex? Is 200, 500 micrometers in diameter. How far are the electrodes? Are centimeters away. So that when you are looking at current that happen inside the mini column, the variation that you have there are very, very small compared to the distance from that mini column to the electrodes of the sensor. So this means when you change, this is the location of the sensor, and this is the location inside the mini column. So when you change this, right, this is remain almost around the same point, the same point. So what happens if I take the center of the mini column, and then I can kind of make a kind of expansion there. So now I'm moving inside, this is a mini column, kind of unrealistic mini column. So I'm moving because all sources that I'm looking now is a current, this contribution of current inside the mini column of the cortex. So these variations are very small compared to this distance here. So I will base everything respect to the center of the mini column, and I can do an expansion of the green function using the Taylor theorem, right? So if you do so, and you substitute in the previous thing, you get this, this expansion here. I don't want you to remember this, but this term here that we have here, we call this macroscopic monopole. This term that we have here, we call it the electrical macroscopic dipole. And this term that you have here, we call it the magnetic macroscopic dipole. So this is important because this is the basic theory that allow you to go beyond what we know today about how the EEG sources are generated, and then make a link to things, to other area of electrophysiology, which is the intracranial recording. People using probe recording from inside the mini column. They also have to apply this current source density there, which is a CSD method, and they obtain currents. But there's no many work today trying to find link between those currents that we have inside the mini column with those that we observe outside the head, right, or in the scalp. So the way that you have to link is this is integral here. And from now on, I'm going to just substitute this integral by this 3 magnitude here, which is the monopolar, dipolar, and the dipole for the electric and the magnetic dipole, which is the other here that I mentioned here, right? So, and this is because I am going to consider a kind of mean field or kind of general contribution of all these cells inside a column. So this current here, this S that you have here, is actually what you get if you perform a current source density analysis using microelectrodes. It's exactly this one. So this creates a link. If you feed a dipole from EEG data or MEG data, in this case from EEG, you get this variable here. If you perform a current source density analysis in a barrel field stimulation paradigm, you get this S here. So you have a way to link these 2 magnitudes, the mesoscopic or microscopic and this macroscopic variable. So this is what you know today. Actually, you know less than that, because we normally remove this term. Since the Paul Nunes in a book in the 80s that based on kind of basic principle of physics, he said that the integral of all charges, if you have a big area, it have to be 0. And by some kind of lack of revision of the literature or kind of misunderstanding of physics, we normally say that these 2 dipoles are the same. So in practical terms, what you have today is that you have to solve this problem here and this problem here. Of course, with all complexity of realistic volume conductors. I'm talking about what the sources create if you are in an infinite and homogeneous medium. Because the other thing is the technical thing. So, so that's the basic physics here in this equation. I just will technically touch base a little bit on what is the electric field, because many people sometimes say the electric field, the magnetic field, and we are, it took me some time to understand what was this, so I'm trying to explain you right now what is the electric field, and it's actually based on the theory that the green function is have symmetry. So you've changed the order of R and R prime, and you get exactly the same. So this is what physics means. So you have the meaning of this. You have a source here and create these 2 potential. this D, delta D, and this delta M here, delta D, E, and the delta M. Now we just remove this source here inside, and I'm going to inject a DC current through these two electrodes. So if you inject the DC current through the electrodes, it will have a conduction current inside the volume. And it's also, if I inject an AC current at a particular frequency, I will get exactly the same, a current inside, which both are conductive current. Now, if you take this magnitude here, well, this is actually the leak field. You have just to normalize by some magnitude. But this J here is what is the leak field. And what the physics of this leak field is telling you is that if you take this J, and you make the scalar product with this JP, which is your neuronal sources, then you get this B here. And if you take this J here and you make the scalar product with this J, then you get this magnitude here. That's all. It's very simple, but it takes time to digest and also to understand the mathematics. So at the end of the day, we always can say that this is given by the scalar product of your sources times something that we call the electric or the magnetic leak field. And these are the definition of this leak field. It's a K. Normally in classic book, and you will see a K. It has some properties that I'm just going to skip now because it's, but sometimes this property help you when you solve this forward problem. So there is a good review of Moshe, and it's a kind of, probably soon we will be 20th anniversary of this, in which it report, it's a summary of all leak field for different volume conductor. For infinite homogeneous medium that we already mentioned before, the EE, the MEG, and then if you use a FIES or you use whatever, they have this beautiful thing. So you can come here and actually look at this and forget all the things that we have been talking. If you want just to program how the magnetic field is created from a dipole, you just come here and use this formula. You need to go to very complex theory. And also you can have these solved numerically, because if you have a realistic volume conductor, your head is, it's not an FE, it's not an infinite medium. You have surface and different conductivity. So you can use what is called the boundary element method and the finite element method. Just we'll touch a little bit what this means. So for example, for the boundary element method, so everything, remember, everything that I present before, all this property of dipole, something like that, was if you have the brain insert in a pool, in an infinite pool of saline. So we call the infinite homogeneous medium. But unfortunately, it's not, or fortunately, it's not in a pool. So it's, it's confined to your head. So in this case, the current cannot go outside the head, and it have to curve. And that is what we need then to solve in a medium. So the first assumption that we have is that your head is comprised of the skin, the cerebrospinal fluid, the brain, and these have different conductivity. But inside this region is homogeneous. So this is called the piecewise homogeneous isotropic volume conducting model. If you have this, and you know the electrodes where they are, you just have to come and take your MRI, do the segmentation of the skin and the bones and all these things, contract this surface with triangles, and then go and solve numerically this. The group that have contributed the most to this is the group from Netherlands. It's theory from the 60s, and I think they already create everything that you need to know. There is a lot of software now that will do this for you in probably 10 minutes. You have just to go and select what are so the main goal of this talk is that you have the wording that you need to go on to a software and say, well, a piecewise homogeneous volume conductor. What is that? So that's what we're trying to create now is a dictionary of things that you need to know conceptually. So you can also assume that the conductivity is not homogeneous inside the brain or inside the tissue, the biological tissue, and then using tetrahedron, then create another level of computation, which is called the final element method. And then you go and instead of having these triangles and things like that, you go inside and create a grid and have to solve numerically. Again, a lot of software do this for you now. So quickly, I will move to the sources. So we have been talking about these forward problem. But let's see a little bit of what is the inverse problem. So now let's assume that, again, we don't have these monopolars. The MEG and AG dipoles are the same. So now we go and using this assumption, I'm trying to solve the inverse problem, which is no other than just giving the sensor the data on the sensor, trying to reconstruct that little dipole. That's the inverse problem. Now we know that there's normally you have situation if you have a single dipole and it's good enough. If you have a patient with epilepsy and in focal epilepsy, sometimes you can use the single dipole model because it's very localized. It's going to at a particular time window. But if not, then you have to start making assumptions how your sources look like. So the most general approach is to say, okay, you have a completely continuous field of current source, and I'm trying to reconstruct this continuous field. A particular case is when you have a dipole, but a general case is when you have a continuous field. So we call these distributed sources, right? Or versus dipolar sources. Dipolar is when you have one or two or three, but they are localized. And distributed when you have this continuous field. The thing changed dramatically because one thing, if you are assuming that there's only few sources, typically you don't know what they are. So you have to estimate their position. And that's the only part that is nonlinear in the inverse problem. So if you have few sources, you have to create very sophisticated optimization algorithm to solve this nonlinear function, or to solve this nonlinear optimization function. Now, if you assume that they are everywhere, so you don't have to localize them. You only need to determine their amplitude. This is linear, but then get another level of complexity. You have many. So in the case of typical multiple dipoles, you typically end with 10 dipoles. Actually, there is a rule. You cannot have the number of sources divide 3 as the number of dipoles. If you have 32 electrodes, you divide by T, you probably can go hardly to 9 dipoles. And except in some cases, VISA have been working on using the temporal data, so assuming that the dipole now is in one direction and it's just changing the amplitude with time. In this case, you can increase the number of dipoles. But if you don't know, if you want to go to this continuous form, right, then you need to solve the linear problem, but you're dealing with thousands of dipoles, right? And it's a linear but very large problem. So I will use here a notation very quickly, a notation introduced by my friend Sylvain Baillet in a very, very good study published in the IEEE magazine in 2001. You can go there, and everything that I'm telling you right now here it will say they are much better. It's one of my, actually have like 5,000 citations. It's something very, very, very good study. So this is the dipole. So a dipole normally have a position. So you have to characterize this with what is called the delta Dirac. So it's 0 everywhere, excepting in that position that have the magnitude of the dipole. So if you use this, then you have that the magnetic field is that Lick field that we mentioned before. Now it's not a magic thing. Times that amplitude of that direction of the dipole, or you have that the voltage is the same, but now you're using the electric Lick field time that dipole. So if you have one is like this, so I'm using the notation that this is my observation. It could be, M could be V or could be the V. So it's just general notation, and this A is the leak field, and this is the source, right? So what happened is I have multiple sources. Now 40,000 of them. Well, I just put them in a column. So normally this says 3 per 1, so it's a vector of 3 components. So this is going to be 3 times number of dipole that you have vector. And this is a matrix, which is a number of electrodes. So this N is electrodes now, or gradiometer, if it's magnetic, and electrodes if it's electric. And then you have this is number of electrodes times 3 times the number of sources. And you can put it in a matrix like this, in the vector. So it's algebra. We came from Maxwell, those things in Taylor, and then we now in algebra, right? So simplify a lot. Now you can have time. So you can have observation at different times in time instant, and then you can come a little bit further. You can then create this matrix of data, and then you have a matrix time a matrix of dipolar moment. You're assuming that they are in the same position, but they change with time, the amplitude. And this is actually what you will see in any paper that you check. Whatever you, normally now, because of this field have a lot of progress, normally we start just saying M, a matrix M is equal a matrix with the leak field time another matrix with the magnitude of the dipoles. And from there, another story starts. What is this story? So the story is that you have to select how you're going to get this solved. So this can be grouped, and it's again from Sylvan. And actually, I will just list and probably say a little bit of each of them. But the whole theory and how to solve what the meanings of each of these is here in Bayet a lot. So they can be grouped in parametric and imaging approaches. So in parametric, as the name says, you just making a model that have parameters that need to be estimated in general. In this case, you solve a linear optimization problem, typically. So least square estimation is when you have dipole, you have multiple dipole, you have to estimate their location, you solve an optimization problem, and typically what you use is a least square approach. Then you have the beam-forming approaches that, of course, create a continuous map, but it's based on an approach that is parametric. And you have this algorithm that was created by Richard Leahy and Mosher some time back, which is the music and actually the rap music. They come a little bit late. Remember, Michael? It was funny. And then you have the image approaches that then what you do is you have to solve this inverse problem of hundreds of thousands of sources, so it somehow is not unique. And then you have to put information, you have to introduce new information about sources. The way we do this, one of the ways we do this is using the Bayesian approach. So the Bayesian formulation is when you combine the optimization problem, where you try to minimize the error, and then you add a term in which you say, okay, my sources, I want that my sources being smooth in space, or they have a minimum amplitude, right? And this is introduced in a mathematical context that is called regularization, which is statistically equivalent to the Bayesian formalism, right? So why you need this? Very simple. So let's say that you have, and I will illustrate this with an electrode, with the electric potential, right? So you have an electrode on your scalp. You have two sources here. So your potential is equal the linear combination of these two sources weighted by the leak field, electric leak field. So this is not unique. You can have 3 times 1 plus 2 times 1, which is 5, but you can have 5 times 1 and whatever times 0. And let's give you 5 again. So this is not unique. So what you have to do is to find a solution in this plane here. So, for example, what kind of solution you have? If you assume that J2 is 0, then you're having the dipole here. But if you assume that J1 is 0, then you have the dipole here. So these two extremes are the dipolar solution, the single dipole solution. Anything that moves in this line, it will produce the same potential, exactly the same potential. So it's not unique. That's what we say. It's not unique. You can come and pick up any of these combination, and it's going to give you the same B. So what kind of constraint we introduce using all these approaches that we were discussing in the previous slides? One is, for example, the minimum norm. We assume that the projection of the zero on this line, the orthogonal projection, this is the minimum norm, which is the solution that have the minimum energy of all these dipoles. If now you take kind of weighted smooth solution, then you get in the Loretta solution. Kind of mean these two, kind of mean, weighted mean. So this is, actually this is, if I remember, I don't know if Pedro is here or no. Pedro, this was an image from 1992 that Roberto Pascual created and have been used by many of his friends. This is a very nice table that Pedro provided me today, in which you have here different type of and that's what I need, a whiteboard. So when you have this penalization term, you normally have a matrix times this vector with the dipoles, which is the current sources. So this matrix is what defines this axis here, smooth, non-smooth. But then, because you are trying to obtain a metric, you need to use a particular way to measure things. So you need to use a metric. And then you have here type of metrics. You have this sparseness, which is called a mathematic L1 type, and then you have here the kind of L2 norm. And if you find if you fill this table here, you have the focus, which is one of the software that we use. You have the minimum norm as introduced by Williamson a long time ago, and Andreas Ioannidis, and we have Loretta from Roberto Pascual, and then you have here what Pedro named Vareta. I don't know why people use not in the case of Pedro and Pascual, but some people use the name of the children, and this has been a tendency, right? Okay, so changing quickly the subject to integration with fMRI, and probably we go, there's no more math in this class or in this course, so this is what we have in the MEG, EG, in that map, very famous map. We have the temporal resolution and spatial resolution. Of course, we observe MEG at very high temporal resolution, but we are very poor here. And fMRI will go a little bit low here, but then it could go to the level of a column of 1 millimeter. So we need to use these two modalities, and it's the less invasive. Here, the color red means kind of invasive. So these are kind of non-invasive, so we try to combine them to take advantage of these two characteristics, highest temporal resolution in one and low in the other, and high spatial resolution in one and low in the other. So we try to fuse them, but then you need to do correctly. So I start with and I think, I don't know if Petra was talking about the neurovascular coupling, I'll probably go a little bit into the more detail here. This is a wonderful recording by Drew, my friend in UPenn, that did a recording in vivo of the vasodilation. And when you look at this, you see that this is the diameter of the arterioles. You look at this, normally you have a little peak here and then another thing, so it's kind of biphasic response. So if you understand a little bit the physiology behind this, so it's kind of first response that many people call this the phasic response. It's based on nitric oxide, prostaglandin, and then you have a second response that we know, or there's some evidence that is what we call the tonic response, that is a pathway involving astrocyte, glial cell. So evidence of these two mechanisms have been provided for years. Starting in the later of 90s, Estrada and Javier de Felipe create this. They did a study that they noticed that there was nitrogen neuron, typically a biologic neuron that release nitric oxide, and normally they're close to the vessel. And these nitric oxide synthase are normally in the terminal of the neuron. So whenever there is action potential coming, there is a release of nitric oxide. There is a very nice validation of the Afonso Silva, in which block with the antagonist the response, and it was able to kill the whole Bolt signal response. Beautiful. So the second pathway, and it's very short summary here, is the one involving astrocytes. So astrocytes have a group in two categories. What we call the neural astrocytes, which are homogeneous distributed, and what we call vascular astrocytes that sometimes are just on top of the vessel. They are pericyte. And they group around vessel, and they have created with the endothelial cell, they create something called a neurovascular unit, very well described by Eddie Hamels in Montreal. So they have several characteristics, but the most important is that they have mechanisms to communicate with the vessel and receive information from neuron very quickly. Whenever you have neural activity, you have consumption of ATP, therefore consumption of oxygen. There's a decrease in tissue pressure for oxygen. And then you have neuroreceptor release. And one of the most important is the glutamate. So first you have nitric oxide, as we mentioned. So there's a nitric oxide pathway from neuron. And then you have these glutamate, that you have a glutamate receptor in these cells that trigger through IP3 response. It's a calcium-induced calcium response mechanism. Trigger calcium response in the astrocyte that mobilize all arachidonic acid from membrane through an enzyme in the membrane, which is the phospholipase 2. At the same time, this acid will travel to the nerve vessel and then produce a constriction there. At the same time, this same acid activates two proteins that is inside the astrocyte, COX-1 and the P450, that both of them create vasoactive. So one of them create the acid, the other create a prostaglandin, they are vasoactive. So from one side you create constriction, from another side you create a dilation. These two mechanisms are balanced by means of exchange of lactate. This is what is called the co-transporter of the lactate and prostaglandin. So when you have too much lactate, we take the prostaglandin inside and reduce the constriction. All these have been very well described. There is a review paper that is here, and you can find all these mechanisms there. So it's linked with glycolysis, it's linked with this effect on inhibition. It's a little bit complicated, just giving a flavor of what this, how complex this, and where you can find literature. Right? So validation of this, there's many, but I want to bring here a very cool one. This is in vivo. This is an astrocyte. This is a vessel. This is from Niedersgar group. It's a Canada paper in Nature Neuroscience. They put cage of glutamate of calcium inside the astrocyte, and with light, very localized, using a laser, they release this calcium. They open the cage, and then they measure the response of the vasculature, the diameter, and you see here the calcium response here in green, and the diameter of the vasculature in red. And they then use a couple of pharmacological manipulation to demonstrate that it actually was a real mechanism. So how we model this part? So we have many ways to do that. One of the most used is the balloon model. There is implementation of this balloon model in software. SPM have one of these parametric versions, in which you have the neural activity here linking to this, what we call inducing signal, that open these arterioles, and then increasing blood flow that cross the capillary bed, and here there's a stealing of oxygen that depend on the gradient of oxygen in plasma and tissue. And then you have this deoxyhemoglobin going here. There's an increase in volume, and at the same increase in the number of deoxyhemoglobin that go in. But you know what happened? It's actually a decrease in the relative concentration of the deoxyhemoglobin, because the volume increased that much that at the end you have a decrease in concentration of the deoxyhemoglobin. Remember one thing, both signal decay when you have an increase in the oxy because it's paramagnetic, right? So it's introduced this inhomogeneity in the field. And they increase, the bold signal increase when you have a reduction in the oxyhemoglobin. So the first response that you have in a bold signal very fast is this increase in volume, therefore a decrease in the oxyhemoglobin, therefore you have this overshoot. Later the vessel will go to the normal position, and then you still have consumption of oxygen by the neuron, and then you have an increase, because same volume, increase in the deoxyhemoglobin, which is very long, sustained, and then you have this undershoot. That's the two mechanisms. You can model this as two Gaussian or two function moving. So if you move too fast, too early, this oxygen consumption, they get the dip, the initial dip that people are familiar with. So this is kind of the equation, the models of the balloon model that was introduced by Richard, many people, but many contributions from many group, but I think the very good paper from Carl Friston in 2000 make kind of a summary. We have been doing experiment demonstrating that if you use the balloon in actually visual, using visual data from visual cortex, it's very linear. That epsilon that we mentioned in the balloon model, this efficacy is linear related to the response in a specific range of activity. Another way to model this is directly linking the blood flow to the diameter using the generalized. Some French here can help me to say the same. Huh? Poisson, right? Something like that. And equation, and then you can model this diameter by contribution of all these pathways that we were mentioning before, the nitric oxide, prostaglandin, the ET, all these pathways with the decay here. And actually, this is something interesting. People are saying, well, it's nitric oxide, other people is the prostaglandin, other people are saying that is the astrocyte. And what I did, I took all this literature, put it in a table, and this allows you to calculate exactly what was the drop in Bolt signal when they used one of these pharmacological manipulation. And I came up with a very, very kind of estimation of the coefficient of each of these contribution. So all of them are present. So in some cases, one is bigger than another. So how many minutes I have? 5. Okay. So this is a recording of both signal and the electrical activity in rat. So you can see very, very good correlation. We use this model to study the board response and this biophysical mechanism. And this is another study in human performed in my lab in which you have a visual stimulation. This is both signal. This is the response of the visual checkerboard. And we have been doing some modeling to determine each component in this response from the dipolar response, each component from where it's coming in the microcircuit. This data have been reported in some time back in the human brain map. And if you're interested in linking a little bit to the Bolt signal response with the data, with the model, sorry. So I think I skip here. Actually I wanted to introduce this, but Thomas was okay, but I cover the part of the EEG and MEG inverse problem with the integration with fMRI. Probably if someone is interested a little bit on knowing more about how we do the modeling inside the mini column, that's what I was going to start talking about now. if someone is interested in this part, how we create this link between the current source density analysis inside, how we use computational modeling, how we go from the neuron, from the Hodgkin-Huxley equation, and we go all the way to the EEG. That's what we're going to talk. If you're interested, you can talk to me after the talk or after this course. Okay? Thank you very much.